Hello. So today what we're going to do is we're going to talk about the quotient of powers and how to handle negative exponents, right? So we're continuing our journey through talking about different ways to handle exponents in types of expressions that we're going to see. So first off, let's just take a look and see if we can figure out what the rule is when we've got a quotient or when we're dividing powers. Right? If I have a to the 7th divided by a to the 3rd, right? Let's think about what each one of those is. When I have a to the 7th power, right, that's just 7 a's all next to each other that are multiplying. Same thing for a to the 3rd, except there's just 3 of them, right? So what I'm going to do is I'm going to write this out as one big old fraction. And up top, I know I have 7 a's all multiplying each other, right? So 1, 2, 3, 4, 5, 6, 7, right? So we have 7 a's all multiplying. A to the 3rd is just 3 a's, right? So a times a times a. Right? So you might notice that I kind of like smooched that over to the side a little bit, right? The reason why is because when we have the same thing on the top and bottom of a fraction, right? You don't need to write this part down, but say I had like 2x over 2y, right? If I have a 2 on the top and the bottom, we can kind of think about them as just kind of like canceling each other out. Right? When we're dealing with exponents like these and variables and all that, we can kind of think of it the same way. If we have the same thing on the top and bottom of a fraction, we can just cross them out, right? So these all cancel each other, right? So what's going to happen is that up top in this fraction, all I have left are 4 a's, right? If we think about other ways to write 4 a's all multiplied, we can just write it as a to the 4th, right? And you might already, like just from that, have an idea of what the rule is, right? If you can, then that's awesome, right? I'm going to take a look at this one that's right below it, right? So we are skipping from A to C, right? I'm just doing the one that's right below here. And this one's where I have 12 y's on the top and 1 y on the bottom, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just barely squeezed them all in. And 1 y on the bottom. Much easier. Right, so what's going on here is the same thing. We can cancel out however many we have that match on the top and bottom. If I look at what's left on the top there, I have 11 y's. That's y to the 11th power. Right? So hopefully what we're seeing is that when you have some on the top and some on the bottom that match, you can kind of think about it like subtracting their exponents. Right? On that first problem, we had a to the 7th divided by a to the 3rd. If we think about that 7 minus the 3 that's on the bottom, we can think about it as a to the 4th. That's what 7 minus 3 is. Same thing for this one that we just did on part C, right? That bottom piece is just 1y. We could think of that as y to the 1st power, like I just added in down there over in this corner. If I have y to the 12th on the top and 1y on the bottom, 12 minus 1 leaves us with that 11 that we found, right? Let's swing over to here. Right, that's going to help us out with B, because I don't really want to write the letter M 19 times, right? 14 on the top and 5 on the bottom. But if I think about it as what's 14 minus 5, that's going to leave me with 9 M's. So M to the 9th. For D, it's a little bit trickier, right? We have 13 on the top and 13 on the bottom, right? They're all going to cancel out. So I can think about that as having N to the 0, right? 13 minus 13. But there is a better way to think about something like example D here. If I have the same thing on the top and bottom of a fraction, right? Say I had 3 over 3. That's the same thing as 1, right? If I had, 4y divided by a 4y, right? That's also the same thing as 1, right? 1 is when you have the same, number on the top and bottom of a fraction, just like we see. In example D here, we have n to the 13th on the top and the bottom. So we know that that can be equal to 1, right? So this is actually a property that we're going to kind of formally state a little bit later on, but just as a sneak peek, something to the 0 power is going to equal 1, right? And that's kind of why, right? It's because if you imagine it, like we're subtracting the exponents, you get n to the 0, but if it's the same thing on the top and bottom in the first place, it equals 1, right? So they're equal to each other. Right, so that's going to lead us into talking about our quotient of powers property, right? So right below all that, the quotient of powers property is going to look something like this. If we have x to the a power divided by x to the b power, then what we can do is we can say that that's x to the a minus b power, right? Just like with some of the other rules that we were talking about last time, it matters that they have the same base, right? So the fact that this is x and this is also x, right, that matters, right? If the top one was x and the bottom one was y, we couldn't do that, right? So you need to have the same bases that match, and your answer is also going to have that same base, with just the exponent part changing, right? So it's something to keep in mind, right? So immediately, it looks like we're just jumping right in, right? This looks pretty awful. 30a to the third n to the sixth divided by 5a squared n. Ooh. So this looks really awful, but it's not going to be as bad as it might seem, right? We're going to take it one piece at a time. And, what we're going to do is we're going to divide the pieces that divide together, right? 30 and 5 are just numbers, right? We can do 30 divided by 5. We're also going to be ending up taking a look at a to the third divided by a squared, right? Those match up. They're both a's. And then last but not least, we got n to the sixth and just n. Those also match because they're n's, right? So when we do this, there's a couple different ways you could think about it. For this first one, at the very least, I'm going to write it out as separate pieces just to kind of show what we're doing. 30 divided by 5 is a piece of what we're doing, right? We are also, it's multiplying with this other chunk, which is a to the third divided by a squared. And then we've got that third chunk there, n to the sixth divided by n, right? So all I did was I split that up into 3 different fractions, one for each piece where they kind of match up together. So what I'm going to do is right below that, we're going to evaluate this, right? We're going to see what this comes out as. So 30 divided by 5, that's going to give us 6. A to the third divided by a squared, right? Using that rule that we were just working on, that's going to leave me with a single a, right? I could write a to the first. Much like a lot of ones in math, right? That one often won't be there, right? It's assumed that if we have an a, there is one a there. We don't really write the 1 that often. Last but not least, if I have n to the sixth divided by n, that's taking 1 away from the 6, so I have n to the fifth. Right? So when I'm getting my final answer here, right, it's just all these pieces smushed together, 6a n to the fifth. Right? So we took each individual piece, did that division, right, and just smushed them together. Right? So hopefully it doesn't seem all that bad. Let's try another one out. And actually, by let's try another one out, I'd like you to try this one out, right? Pause here, give it a go. So hopefully you gave it a shot, right? We got 40 divided by 8, right? So I'm going to try and, simplify this a little bit faster, right? So on the last one, we broke it up into 3 fractions and did each one individually. I'm going to try and do this a little speedier, right? This is what we want to try and work towards. If you split it up into individual ones and did it just like example 1, that's perfectly fine. Right, so what I'm going to do is 40 divided by 8, right? That's going to leave me with 5, right? So 5 is what I got out of that yellow piece. Next up, we have b to the 10th divided by a single b, right? So 10 up top, take away 1 that's on the bottom, leaves us with b to the 9th, right? That's what we're getting out of that blue piece. Last but not least, we got c to the third and c squared. If I had 3 up top and 2 on the bottom, right, 3 minus 2 leaves me with a single 1c. And again, the 1 is optional. So 5b to the 9th, c, is what we're trying to get to, right? And again, hopefully that doesn't seem so bad, right? We're just subtracting the bottom number from the top number when they've got exponents. Something that, I guess I should probably talk about, because it seems like it's a little tricky sometimes, is that if I have something like 40 over 8, right, we're not subtracting those, right? That's just regular old division, right? 40 divided by 8 is 5, right? Don't get 2 in your head and write down 32, because that's not what it is, right? So numbers still divide like normal, right? It's when we're dealing with exponents that we think about it as subtraction, right? So there is a difference there, right? So just something else to be careful of, as if there wasn't enough already. Right, we're going to talk a little bit about scientific notation. Right, so scientific notation you may have run into in the past, obviously in science class, or possibly even in social studies. It's when we're rewriting decimals or large numbers as multiplication by 10 that then gets raised to a power, right? The decimal must be between 0 and 10, right? So if I wanted to rewrite 87,800,000 in scientific notation, what we're going to do, and you might remember this again from previous math classes, is that right now, that in this problem, my decimal point is right over here, right? It's right at the end of that last zero. I need to start moving that decimal point, right, so that we can get a number that's between 0 and 10. Right? So I'm just going to count how many times I need to hop it to the left. Right? So it's 1, 2, 3, 4, 5, 6, 7. If I hop 7 spaces, right, then that's going to give me 8.78 with a bunch of zeros after it. Right? So 8.78, and all the zeros, we just kind of, forget about them. So why are we doing that, right? So you might be like, what the heck is the point of that? So when we're writing things in scientific notation, right, it's just a way to, kind of help us eliminate a bunch of zeros and deal with a slightly easier number, right? If you're talking about like, this was 14 quadrillion, 6 trillion, 9,400,005, there's a whole lot of digits in there. That's a lot to keep track of. But if I can put that down to 8.78, right, that's much nicer. So when we're doing scientific notation, right, we have that decimal and we're multiplying it by 10 raised to a power. So multiply by 10, and then the power that we raise it to depends on how many spaces we had to move our decimal point, right? Because I moved it 7 spaces, that's going to be 10 to the 7th, right? If you happen to have a calculator handy, if you type this in, right, if you type 8.78 multiplied by 10, and then you might have to hit like this little up arrow key, 10 to the 7th, that should spit you out with 87,800,000, right? We were just rewriting the number, and it's a little bit easier to work with there, right? You may not believe me. You might be like, wow, this seems like a lot of work to just change a number, right? But there are places where it's actually pretty helpful to be able to write this in a different way, right? Let's try rewriting 956,400,000,000 using scientific notation, right? The numbers are pretty big. So again, first things first is I want to move my decimal point until it turns this into a number between 0 and 10. So, we can jump a little bit. So that's 3 spaces, 6 spaces, 9 spaces. Oops. I didn't think it would do that to me. So 3, 6, 9, 10, 11 spaces. Right? So most of the time what we're going to be doing is we're trying to get the decimal point all the way over until there's only one number that's in front of it like that. Right? So now 956,400,000,000 is now 9.564. Right? And again, we got to multiply it by 10 to a power, right? And that power again is how many spaces we had to move the decimal point. So again, if you plugged that into a calculator and your calculator was willing to let you, have that many digits there, right, you'd end up exactly where we started. That's also another benefit of this is that, using calculators, they're a great tool. Your calculator most of the time cannot handle you typing in 956,400,000,000 with all those digits, right? So if you rewrite it as scientific notation like we have, then you can actually use it in a calculator. All right, so let's actually do some problems that use this, right? Flippery-do on to the next side. So the gross domestic product, gross, GDP of a country is the total value of all the goods and services produced in that country. When the GDP is divided by the population of the country, the result is the GDP per person, often called the GDP per capita. In 2006, way long, ancient times, Denmark had a population of about 5.5 million and a GDP of $243.4 billion. We want to figure out what is Denmark's GDP per capita, right? So we are dividing the population by the GDP. Let me back up. We are dividing the GDP by the population, right? When the GDP is divided by the population of the country, we get the GDP per capita, just like it says in there. So a couple important bits, right? I need some numbers. The population was 5.5 million. The GDP was 243.4 billion. Right? So what we're going to do is we're going to start off by just writing those numbers out. We're dividing the GDP by the population. So up top, we got GDP, 243 billion 400 million. Right? That's a big number. We're dividing that by the population, which was 5.5 million. Right? And I'm going to try and line my digits up. Right? So, again, your calculator probably won't let you type in 243,400,000,000. So this is where scientific notation comes in handy. Right? What I'm going to do is I'm going to convert each of those numbers to scientific notation. Right? The top one, I'm doing 3, 6, 9, 10, 11 jumps. Right? So it's turning into 2.434 times 10 to the 11th, right? Because again, 11 jumps. That's where we get that 11 from. I'm then going to divide that by whatever we do with the bottom, right? So there's 6 jumps there for that decimal place. Right? So this is now 5.5 times 10 to the 6th power. Right? So 2.434 and 5.5 definitely numbers your calculator can handle. Right? So what we're going to do is we're just going to equal that out, and we're going to see what it comes out as. Right? So 2.434. Whoops. Oop, no, I need the other one. Hold on just a second. Get to see my home screen for a quick minute. Okay, so back to here. We'll pop this over to the side. Perfect. So 2.434 times 10 to the 11th, right? But what we're going to do is we're going to take it one piece at a time, right? Just like the problems we were working on a little bit ago, I'm going to multiply divide the pieces that go together, right? So this is just a number, and this is just a number, right? Over on the other part, we have 10 to the 11th power, right? So we are going to treat that as its own set, right? 10 to the 11th and 10 to the 6th match up pretty nicely. So 2.434 divided by 5.5. That's going to give me that number there, which is 0.44. Let's round it to 3, right? That's what we get from dividing those yellow pieces, right? And again, my calculator was pretty easy to handle, right? For the blue piece, right, 10 to the 11th divided by 10 to the 6th, well, that's where our new rule comes in handy, right? So 10 to the 11th on the top, 10 to the 6th on the bottom, right? Think about those 10s as kind of canceling out like we were doing with the variables. We're going to have 10 to the 5th left over there. Right? So from here, what we can do is, again, calculator is going to be helpful to us. There are two different ways we could actually approach getting our final answer for this. We could do, 0.443 times 10 to the 5th power, right? That's going to give me 44,300, right? Or what we can do, right, is we can take a look at, what's going on with the decimal place, right? So in our answer, my decimal point is right there, right? It's times 10 to the 5th power. So when it's times that to the 5th power, that means that to undo the scientific notation piece, I can then move my decimal point 1, 2, 3, 4, 5 spaces backwards, right? So that's where those extra zeros are coming from, right? It's like I moved my decimal place 5 spaces to the right to get rid of that 10 to the 5th, right? So that's one way that we can use scientific notation, right? This is GDP, so it's money per capita or per person, whichever way you want to say it, right? Let's try another one of these, right? So we got the land area of China is 9,596,960 square kilometers. In July of 2006, again, ancient history, China's population was estimated to be 1,313,973,713 people. What a number. What is the population density of China in people per square kilometer? Right? So, obviously, a whole bunch of numbers here. To figure out the population density, we're going to be taking that population and dividing it by the land area, right? So we're going to take population, which is this big honking number, and divide it by land area. All right, so let's write that out. So population, 1,313,973,713 313,973,713, all divided by the square kilometers, which is 9,596,960. Gross. Those numbers are awful. And again, your calculator might not let you plug in 1,313,973,713. So, scientific notation, going to be pretty handy for us here, because I don't want to do this any other way. So on the top there, we're going to, again, drag our decimal place, right? 3, 6, 9 spaces to go over. Right? So I'm going to rewrite that number as 1.31, and then there's so many numbers that I'm just going to round it off, right? When I'm rounding it, I'm going to turn that into 314, right? We're multiplying by 10 to that power, right? So we moved it 9 spaces. That's where I get that 9. And then pause here, try and figure out what the second one should be in scientific notation, right? It's okay to kind of round it off a little bit. So hopefully gave that a shot. All right, we're moving it 6 spaces over. So I'm going to get 9.59, and then I'm going to round it off to 7. Times 10 to the 6th power. Right? And again, this is where our calculator is going to be nice, right? I don't want to do that out in my head or by hand or whatever, right? So we're going to do same thing on the last one. All right, we've got this yellow piece that we're going to divide by this other yellow piece because they kind of match up. They're both nasty decimals. Then we got these blue pieces that match up. They both got 10 to a power. So 1.314 divided by 9.597. Whew, yeah, I don't want to get that on my own. Oops, that's going to be 0.13, let's call it 7. All right, we're doing lots of rounding, so our answers aren't going to be absolutely perfect, but they're going to be pretty all right. All right, so again, that's the piece that we got out of the yellow there, right, dividing those 2 decimals. The next piece is when we have 10 to the 9th divided by 10 to the 6th, right? And again, what we need to do is think about it like that rule we were practicing on the front. If I have 9 tens on the top and 6 tens on the bottom, some of them cancel out. I'm left over with 3 tens, so 10 to the 3rd power. Right? That's what we're going to have left over out of that. So from here, again, to get our answer, we can do it 2 ways. We could type this in right into the calculator, or what we could do is, like I was saying, this 3rd power means that I could just move my decimal point 3 spaces back towards the right. So 1, 2, 3. If I move my decimal place 3 spaces over, I'm going to end up with just 137. Right? Which, looking at where we started, right? Hopefully using the calculator made that a little bit easier than trying to do it out any other way. Because we're talking about population density, this is people per square kilometer, or kilometer squared. All right? So scientific notation is one way that property is really handy to us, right? We can also handle problems, and again, I know I'm flipping back. We can also handle problems that look like these that we were practicing with before, right? Match up the pieces that go together, divide those, and that's where we're going with it, all right? So I'm going to skip ahead a little bit back to where we were. So now we're going to talk about negative exponents, right? And it might seem a little spooky, like, oh, negative numbers are awful. Negative exponents must also be bad, all right? But let's take a look. If I have 2 to all these powers, let's kind of fill in some of the ones we know. If I have 2 to the 1st power, that's just going to be 2. If I have 2 to the 2nd power, right, 2 squared is 4 because we multiplied by another 2. 2 to the 3rd is 8. It's 3 2's all multiplied. 2 to the 4th is 16, right? So every time we went up 1, right, we multiplied by 2. So let's think about what's happening as we go down a power, right, to get from 16 to 8, right? You can think about it as like, oh yeah, we had to subtract 8 to get from that. But then that rule doesn't work if we do that next step, right, to go from 8 to 4. We only subtracted 4. To go from 4 to 2, we only have to subtract 2, right? So we don't want to think about it as subtraction, right? What we can do is we can think about it as division, right? To go from 16 to 8, we had to divide by 2, right? We were taking away one of those 2's that we multiplied by, right? So we divided by 2 again, and divided by 2 again, right? If I keep dividing by 2, that's how I'm going to keep like stepping down with these powers. So 2 divided by 2 is going to leave us with 1. 1 divided by 2 leaves us with a half. A half split in half. So 1/2 divided by 2 is 1/4, right? If you're getting a little like, ooh, I don't know about that, right? If you think about, having some sort of like a pizza, if I had half and I split that in half just like that, all I'm left with is 1/4, right? So that's where we get that. Moving on down, if all I had was a fourth and I split that in half again, right, and all I've got is this piece right now, that is 1/8, right? So we're dividing by 2 again. Right? So when we get into negative exponents, right, we end up having fractions actually, right? So something that we can do here is we can kind of set ourselves up with a rule that will be helpful. You might notice that 2 to the negative first power is kind of similar to 2 to the first power, right? Same thing all the way down, right? 2 to the negative third power is sort of kind of similar to 2 to the regular third power up top, right? Like those numbers on the bottom match. So what we can do is we can set ourselves up with this rule, right? This is the same thing as 1 over 2 to the first power. This is the same thing as 1 over 2 to the second power. And this is the same thing as 1 over 2 to the third power, right? So that's going to help us write our negative exponent property, right? So I'm going to try and keep it all on the screen at the same time. If I have x to the negative a power, right, what I'm going to do, and I can make that equal to 1 over x to the positive a power, right? So whenever you have a negative exponent, you flip it to the other side of a fraction, right? And you can make that exponent positive, right? Something kind of similar happens, right? And we'll kind of draw a little divider line here. If I had 1 over x to the negative a power, right? If that negative power was on the bottom of a fraction already for some reason, then what I can do is I can flip it to the top and make it positive, right? When I do that, right, we know that anything divided by 1 is just itself, right? So again, whenever you have a negative power, flip that thing to the opposite side of a fraction and change that exponent to positive, right? That's what we're doing here. So let's try that out. Let's try that out with a couple of these. So this one on the left, a to the 7th times b to the negative 4th, right? So a to the 7th is fine, right? It can just stay as a to the 7th. When I'm doing b to the negative 4th, right, again, what I want to do is I want to flip it to the bottom of a fraction and make that exponent positive. So it's 1 over regular old b to the 4th. When I simplify this down, right, when I smush these two things together, anything with a regular old positive exponent goes on the top of a fraction, and anything that was kicked down to the bottom goes on the bottom, right? Let's try out that second one here, right? C to the negative 8th is going to turn into 1 over c to the positive 8th, right? We're flipping it to the bottom, making that exponent positive. D squared is fine as it is, right? So again, when I smush those together, d squared is regular old d squared that goes on the top. Anything that was kicked to the bottom stays there, right? So there is a third one over to the right. Pause here, try that one out, see how it goes. It's not going to hurt, I promise. Well, maybe a little bit. So hopefully you tried that out, right? So we're going to do it the same way. I'm going to treat it just like the last couple problems. W squared stays W squared. Nothing funky going on there. X to the negative 4th, we're going to flip it, right? It's going to turn that into a positive. Y to the negative 3rd, same thing. We're going to have to flip that to the bottom. And then z to the 7th stays z to the 7th, right? Nothing going on with that. Right, so now what I need to do is smush all of this together. So just like on the last two, anything that was a regular old like w squared or z to the 7th is going to stay on the top, right? Anything that was kicked down to the bottom is going to stay there, x to the 4th, y to the 3rd, right? So, hopefully that made some amount of sense, right? If it did, give yourself a pat on the back, because if you take a look at what we started with, right, like that looks awful. Our answer also kind of looks terrible, right? But we just worked with both of those things, right? Which is pretty impressive if you think about it, right? Think back to you like 10 years ago doing math, and then think like, oh man, look at that, right? So we got a little bit more to do, right? I know I'm kind of going a little long on this one, but I will try to speed myself up and stop talking so much. We have a negative exponent property for fractions. There isn't like a fun way to discover it or anything. We're just going to kind of go at it, right? If I have something like this, so I'm going to have a big set of parentheses. If I have x divided by y, all in these parentheses, and then it's raised to the negative a power on the outside, right? The way that I'm going to handle that is I'm going to, still have it in parentheses. I'm going to flip that fraction and change that to a positive exponent, right? So it's kind of like flipping things to the opposite side of a fraction like we were doing on the last couple problems, right? Except we're flipping the fraction itself, right? So all we're going to be doing here, right, is just that. So if I have 5 over 4 to the negative 2 power, right, what I'm going to do is I'm just going to flip that fraction to be 4 over 5 to the second, right? We can kind of talk a little bit about how that's going to go if we wanted to simplify that, right? If I have 4 over 5 squared, that means that I have 4/5 times another 4/5, right? When we multiply fractions, right, as you've run into in the past, the top multiplies the top, the bottom multiplies the bottom, right? So this is what we could get out of that as our answer, right? On the second one, there's a little bit of a typo. That should be m to the second power, right? That's m squared, not m with a 2 next to it, right? So same old deal, though. I'm going to start by flipping this over. Right? It's going to be m squared on the top, 1 is on the bottom, and that 3 is now a positive 3, right? So after this, again, I've got m squared over 1. That's the same thing as just m squared, but it's still to the third power, right? Using those properties that we learned about last time, right, I know that m squared to the third like that is going to be m to the 6th, right? And as we're going through these problems, you might notice that like I'm doing more than just the property we're learning about, right? That is part of this, right? We're trying to simplify these as much as possible using all of the properties that we've been learning about, right? So if you can go further with it, do that extra step, right? Figure out what it's going to be, right? So same kind of deal on this one. I'm going to flip the fraction over. It's going to be 2 over 3 to the positive 4th power, right? Same kind of deal as that first one we did, right? Except now I've got 4 of these all multiplying, right? So a bunch of 2/3 all multiplied together. Up top, we multiply all those 2's. 2 times 2 times 2 times 2 is going to give us 16. 3 times 3 times 3 times 3 is going to give us 81, right? That one grows quite a bit faster. All right, so 16 over 81 is what we'll get out of that, right? If you want to use a calculator to help you with any of those ones, perfectly fine. Calculators are there for us to use. Last bit here, right? We're going to flip that fraction. Sounds like a game show. Flip that fraction. Okay, so we got k to the 4th divided by 1 all to the 5th, right? Just like the second one in there where we had the m's, this is just k to the 4th to the 5th on the outside. We can multiply those exponents to give us k to the 20th. All right, so again, this is something that we want to do, right? Simplify as much as you can. All right. We got 2 awful problems left, and by awful, I mean they're not really going to be all that bad. We're going to take these one step at a time, right? So we're going to kind of mishmash both of the properties that we've been working with. So first up, we've got 5 and 15 that match. We've got a to the 4th and a to the 11th that match. We got b to the 7th and b to the 5th. And then I need to go into another color. C's are in green. All right, so one piece at a time. If I have 5 over 15, right, it's not going to come out super cleanly, right? Don't say 3, right? 5 divided by 15 is the same thing as 1/3, right? So 1/3 is what we're going to get out of that first chunk, right? After that, we're looking at the blue piece, a to the 4th, and then a to the 11th on the bottom, right? So our property that we were working with on the very first page of this was telling me that I can subtract those exponents. So 4 minus 11 is negative 7. Right? That's what we're going to get out of the blue piece. For the b's, 7 on top, 5 on the bottom. Again, we're going to subtract those. B squared. Right? And then last but not least, we've got the c's. 2 on the top, 3 on the bottom. So 2 minus 3 is negative 1. Right? So I know that I've said that the 1 is optional. When it's a negative 1, we do want to write that because that's important, right? If it was a positive 1, it's like, yeah, no, it's assumed that it's just a 1 C there. But if it's negative, make sure you got that, right? So from here, then we just do some of the problems that we were working with, with our last property, right? Anything that has a negative exponent kind of gets kicked to the bottom of a fraction, right? So what I'm going to do is I'm just going to draw one big fraction. We're going to fill things in where they're supposed to go. The 1 in that yellow piece is on the top of the fraction. The 3's on the bottom. Cool, so that part's done. When we have a to the negative 7th, I know that that should go to the bottom, and that 7 should become positive. When I have b to the positive 2, that's fine, right? Keep it up top. And then when I have c to the negative 1, that negative is telling me that I need to put it on the bottom, and it's just to the first power, right? The positive 1, right? So where we're at right now, you could leave your answer right like that. That's not incorrect. We can simplify it a little bit more, right, if we wanted to be real picky. The 1 that's up top, 1b squared, we can just write it as b squared. On the bottom, we have 3a to the 7th, and that, again, because that 1 is now positive, it's optional. You don't need it there, right? So that's what we're trying to get to, right? If you made it to here, still awesome, right? Like, that's not a bad thing. Like I said, your answer is not incorrect. Right? If we can get to that last box, that's great, right? If we get to right here, that's still really good, right? So I'm going to leave this problem entirely up there, right? If you need to go back and rewind a little bit and think through it again, go for it. But what I'd like you to do is really just pause here, try out number 10, right? It'll be a little bit tricky, but go through it the same way we just did this one. All right, so if you haven't yet, please pause and try that. If you did, then great. Let's take a look. So first things first, I've got this 3 and this 12. If I'm thinking about 3 divided by 12, don't say 4, but it is like 1/4. Fourth? What am I talking about? Fourth. Right? Second piece, we've got x squared and x to the 4th. If I think about that, 2 minus 4 with those exponents is going to leave me with negative 2. Right. Third piece, oops. Third color highlighter, please. There we go. We got a y up top and 3 y's on the bottom. So again, if I think about that 1 on the top as y to the 1st, 1 minus 3 with those exponents brings me to negative 2 for that. Right. And then last but not least, right, we've got z to the 6th on the top, z to the 4th on the bottom. 6 minus 4 is 2. So we can treat that as z squared. Okay, so hopefully that was the harder part, right? After this, we're just going to ignore what we started with because who wants to look at that anymore? And I'm just going to put these into a big fraction wherever they're supposed to go, right? So in the yellow piece, the 1 was on the top, the 4 was on the bottom. Let's put those where they're going. For the x's in blue, it was negative, so it's going on the bottom. And that exponent is now positive. Same thing for the y's. It was negative 2, so we're going to put it on the bottom. And now it's to the positive 2. Last but not least, we've got z squared. It's just a regular old z squared. So that goes up top, right? The only thing, if I wanted to clean up this problem, right, and have a really nice looking final answer, is I would get rid of this 1 that's in the front, right? So if you leave the 1 there, it's not going to hurt anything, right? If you want to get rid of it, might be a little better, right? But that's what we're trying to get to. Z squared over 4x squared y squared. Right? And again, if you're feeling even, like if you kind of get this and you're like, oh man, I don't know if I really get it, and you're feeling down about it, think about, again, like you even like 3 or 4 years ago, if you looked at that problem and you were like, oh yeah, I can turn that into this, right? You'd be like, you're insane, man, right? But hopefully it went pretty all right, right? We can do this. All right, we got one last little bit down at the bottom, so you might see that I scribbled out a bunch of stuff. That's on purpose. We got this zero exponent property, right? So way back at the beginning, we were talking about n to the 13th divided by n to the 13th and how that equals 1 and all that. This is where it all comes together. If we have x to the 0 power, that's just going to equal 1, right? It's also going to work if I have like x to the 4th, y to the 3rd, z to the 15th, all of that to the 0 power. If it's to the 0 power, it equals 1, right? That's it. That's all we got. All right, so I know I've been talking for quite a while. I'm going to stop talking and let you go. Please be sure to ask if you have questions on this, right? Some of these can be a little bit tricky, so be sure to ask when I see you, and I'll see you next time.